This conference will now be recorded.
So very good evening, students. Today we are back with the discussions of previous year JEE paper, and today we'll be basically discussing questions from modern physics, and we'll be covering atomic physics, nuclear physics, dual nature of matter and semiconductor. So these questions we'll be picking up and discussing. So we have few questions today for discussions. Let us try to understand the question and solve this. So this is the question from JEE Advanced Paper 2017. So let us try to understand this question and solve this. An electron in a hydrogen atom undergoes a transition from orbit with quantum number Ni to another with quantum number Nf. Vi and Vf are respectively initial and final potential energies of the electron. If Vi by Vf is equal to 6.25, then smallest possible value of Nf is how much? So that is the question. So look here, the question is saying that suppose there was there is an electron in some Ni orbit, okay, and let us say this is Nf, and there is a transition happens, okay, for an electron transit from Ni to Nf. Now the potential energies of this level and this level are Vi and Vf, and their ratio is given. You have to find out what is the value, smallest possible value of Nf. So look here, we need to understand that energy of hydrogen or hydrogen-like atom here it is hydrogen, so we'll see. So hydrogen in general, it has energy minus 13.6 by n square, okay. If we take the magnitude, so we can say that E is directly proportional to 1 by n square, okay. And again we know that the potential energy V is twice of that of the total energy, twice that of total energy, okay. So can we say that V is directly proportional to E? Answer is yes. So kinetic energy and potential energy both has the similar variation, okay. So what we try to mean with this, I'll just write it here. If the let us write this potential energy initial by final is equal to, we can write EI by EF. This we can write from this particular. So this is the total energy, okay. This is the total energy of hydrogen atom, which is directly proportional to, inversely proportional to the principal quantum number, inversely proportional to the square of the principal quantum number. And potential energy has a relationship with the total energy in this way. This is the relation between potential energy and the total energy. So I can say potential energy is directly proportional to the total energy. So if we go in that way, I can write this relation. Okay, again it is given, this is 6.25. Okay, or we can write, see, we'll now write in terms of this EI and EF, in terms of this. So EI, we can write, this is 1 over Ni square divided by 1 over Nf square is equal to 6.25, right? Similarly, then we can do a little bit of simplification as this 6.25. So this is left hand side square. I can just make it whole square is equal to this. So Nf by Ni will be 2.5. So this is the value. Now this can be written as 5 by 2 as well. Okay, so I'll just use this space I'll use. So what we have got, we have now got this Nf by Ni equal to 5 by 2. Okay, so Nf will be 5 if Ni is 2, right? And this is the value of Nf. This is the smallest value of Nf. Okay, so that means the transition is happening towards higher energy. Okay, so this is how we have to solve this problem. So the Nf value of Nf is 5. We'll go to the next problem. This is a lengthy problem. We have to first of all read the problem properly, and then we will try to understand, like, solve this problem. So the electrostatic energy of jet protons uniformly distributed throughout a spherical nucleus of radius capital R is given by this. Okay, so electrostatic energy of jet protons uniformly distributed over this. Okay, so this is the expression of electrostatic energy of jet protons uniformly distributed over a spherical nucleus of radius capital R. All right, now measure masses of neutron. One is neutron and one proton, and then nitrogen, nucleus of nitrogen, nucleus of oxygen are given. So these are the measured masses. You can see this is the mass of neutron, this is the mass of proton, this is mass of nitrogen isotope, and this is the mass of oxygen respectively. Given that the radii of both this nitrogen, see here, nitrogen is this, oxygen is this, so nitrogen and oxygen isotopes, they both have same radius. Okay, so they both have same radius. That is what is the assumption we need to make here according to the question. So given that the radii of both the N and O nuclei are same, So 1 U is 931.5 MeV divided by c square. C is the speed of light, and E square by 4 pi epsilon naught. This can be taken as 1.44 MeV femtometer. Excuse me. Assuming that the difference between binding energies of this and this are purely due to electrostatic energy, the radius of either of the nuclei is how much we have to find out from, like we have to find out whether like which option is correct. I'll try to make you understand this problem once again. See, this is the electrostatic energy for an electron, sorry, for a nucleus which has Z proton, okay, distributed over the surface. So I have now two nucleus, this one and this one, okay.